Hello once again, class, and welcome to another mock lecture. Today we're going to be tackling extrema, which is part of the Intro to Polynomials video series that I want to do for you guys. And I think that we should probably start off with what even is a polynomial. Well, here's its definition. A polynomial of degree n in terms of x can be represented by f of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2. And we're going to keep decreasing n's value until you get down to a sub 2x squared plus a sub 1x plus a constant a sub 0. Every single one of these a sub k's, right, a sub n minus 1, a sub n minus 2, a sub 2, a sub 1, even a sub 0, those are all real number coefficients. So there's no imaginary stuff going on here. A sub n also can't be 0, because if it's 0, then this term is gone, and then it's actually not of degree n. It'd be degree n minus 1. So we have to stipulate that the leading coefficient can't be 0. More good news is that n is some positive whole number. So if you have something like 3x to the 1.7, that's not a polynomial, right? It has to be a whole number up here. So you could do the 11th or 17 or 6, can't even be negative. Like if it's 3x to the minus 11th, that's also not a polynomial. So we're only looking at whole number stuff. And then I kind of already mentioned this here, but a sub 0 is some real number constant. Now, I intentionally went out to 2 here in descending order because this you have seen before. It is a quadratic, right? A quadratic is a polynomial of degree 2 because it goes a sub 2x squared plus a sub 1x plus a sub 0, except we call those coefficients a, b, and c respectively. But a quadratic is a polynomial. In fact, so is a linear function. Y is equal to mx plus b, right? Is like, that's a b, is like a sub 1x plus a sub 0. Here's another one that's a little bit more complex. It's a 4th degree polynomial. We call it a quartic function. N is 4 because it starts, its highest power is 4, so the degree of this polynomial is 4, and then that power descends until you get to 0. One thing you'll notice actually about this polynomial is that there's no x squared term. It is technically there. In fact, if I label all of the a sub k's in this polynomial, we have a sub 4 is 7, a sub 3 is negative 12, a sub 2, which is the x squared terms, the coefficient for the x squared term, it's there, it's just a 0. It is important to know that it is a 0 though, because once we start doing calculations with these polynomials, it's going to be important to put in that placeholder. Otherwise, things can sometimes get misaligned, and like I guess what I'm thinking about is dividing polynomials. It'll be important to have that there when we do that. Now, what do these things look like? Turns out they look like curvy lines, basically. I put 3 of them on here, and I probably should have put a quadratic as well, because a quadratic is also a polynomial function. In fact, we could even put a line if we wanted to. But all of these things have similarities that we're going to be talking about in the next few videos. First of all, they all have x-intercepts, which just like quadratics are going to be solutions to when the polynomial equation is equal to 0. Sometimes we actually call them zeros, but they're x-intercepts. They all have turning points, right? A parabola just has one, and we give it the name vertex. So these have, in that sense, multiple vertices. But they have turning points, right? Their slope is changing from negative to positive or positive to negative. At their ends, they all have some overall direction. So after it's taken care of all of its turning points, they eventually just do one thing for the rest of its existence, either to the right or to the left. This polynomial down here, I had truncated and put some endpoints on it, but if I did not truncate it, it would indeed have some arrows that eventually just do the same thing forever and ever. That's called end behavior. We're going to have a video on that as well. And then doubling back to this turning point thing, we can classify them as high points and low points, and that's what we're talking about today. Those are extrema. And it turns out there's only 4 types of extrema, all 4 of which are illustrated in this one graph here, so let's go through it. The first one is called a global or an absolute maximum. And I'm going to go through the concept image of this stuff first before I talk about the stipulated definition so that it'll make a little bit more sense when we get to that. But a global or an absolute maximum is basically the highest y value on the graph. So whatever this is, I called it c. So let's say you have an x value c that's producing this f of c value. That f of c value is the highest y value on the graph. You could pick any other x, pick this x here. And it's going to give you an f of x value right here that is smaller than f of c. Every single x value will produce a y value smaller than that one, and that's why we call it the absolute maximum. In the same light, there exists an absolute or global minimum, which is the exact same thing, except now it's the lowest y value of the graph. So there exists some c value that produces an f of c value that is smaller than any other f of x value on the graph. And visually, you can see it here. But then we have things called relative or local maximum, or relative or local minimum, that are basically defined almost exactly the same as absolute or global extrema, except for the fact that it's not the highest y value overall, it's the highest y value kind of in its vicinity. So I put a high y value relative to its surroundings. So I usually envision like a bubble of arbitrary size, and there exists a c value inside that bubble that produces an f of c value that's higher than any other f of x value that you could produce with x values that are near c. Okay, so none of these other x values are going to give you an f of x value that's bigger than our f of c. Right? They're all going to be smaller than it. So inside its vicinity, it's the highest y value. And then same thing for relative or local minimum. Inside its little bubble, it's the smallest y value. No other x value produces an f of x value that's smaller than the f of c that I've drawn here. Another kind of quick shortcut that I use for relative extrema. Relative maximums are always this hill type of shape, and relative minimums are always going to be a valley type of shape. And you'll notice this one actually has two valleys. And so we'll talk about this is maybe more than an absolute extrema as well here in just a second. The thing to keep in mind is that all of these things are only y values. So one thing we're going to do is we're going to list the extrema that exists in a graph, and I'm only going to be listing the y values when we do that. Okay, so keep that in mind. We do not need to list coordinates. I don't really care about what the x coordinate is here that produces this maximum. I just need to know what is the highest y value in the entire graph. What's the absolute maximum? Well, it's just whatever this number is. Sometimes you're asked, well, where does that happen? But for right now, we're not concerned about that. Now, here are the stipulated definitions. And I think just showing this to you can be a lot to take in. So maybe let's just focus on one of them here, and then I'll explain maybe one of the globals and one of the relatives. So maybe we'll start with this one. Okay. So the definition says f of c is an absolute minimum if f of c is less than or equal to f of x for all other x's in the domain of f. So we're talking here, right? Here's c. It's really hard for me to draw straight lines like this. Here's f of c. What this is saying is this value is smaller or the same as any other f of x value. So look at the entire rest of the range. Well, f of c is the smallest one. There's no other x value in the domain that would produce a y value that's smaller than f of c. That's what's making this f of c the absolute minimum. If we focus on maybe number 3, okay, so here we're talking about a relative or local maximum. It says f of c is a relative max if f of c is greater than or equal to f of x for all x that are near c. Now, near c is pretty vague, and so you can really make this neighborhood, if you will, this little bubble, as small as you want. Like I could just look around like this vicinity, and it's still the highest y value. That's what's making it a local maximum, that it's the highest y value inside of its little vicinity. But none of these other x values produce, even inside this little bubble. Maybe now we're saying only this is the stuff that we're classifying as near c, just within here. None of those x values give you an f of x value that is bigger than f of c. That's why this is a relative maximum. Okay, so I hope that makes sense. Now let's go over some special notes with extrema. The first one is that endpoints can't be local extrema. They can only be absolute extrema or kind of nothing, which is kind of what this one is. It's just an endpoint. So you might ask, well, why is that? Because I can draw a bubble around it and I can say, oh, look, the y values that are near this particular, what we would say is a maximum, are all smaller than it. But again, look at the definition. So here we're focusing on this one because we're supposing it's a maximum, right? That should be the hypothesis here. It looks like a maximum. Well, if you draw a bubble around it, notice that it says f of c is a relative max if f of c greater than or equal to f of x for all x near c. Well, here's an x value that's near c. It's inside the bubble, but we don't know anything about its f of x value. right? X is not even in the domain of this thing. And so because it's near C and we can't say this because we actually don't know anything about it, it does not fall into the definition of what a local maximum is. So an endpoint can only be an absolute extrema, like in the case of this one, or it's nothing at all, like in the case of this one. Nothing is maybe harsh, it's the end. It's the end point of the graph, and then that's all it is. All right, the next note is that some absolute extrema double as a local extrema, and that would be when an absolute extrema also satisfies the definition of a local extrema. Well, let's consider then number 2 here, and I put the definitions for the global minimum and the local minimum just so that we could look at them side by side. We already discussed how it satisfies being an absolute minimum because it's the lowest y value that's on the graph. But consider that it's also a valley. So that means that anything that's near C would similarly give us things that are bigger than f of C, right? F of C is not only is it the smallest overall, it's also the smallest in its neighborhood. So it also satisfies the definition of being a local minimum as well. Okay, this is basically going to happen anytime the absolute extrema is a hill or a valley. If, let's say, this came up to like here, above what was previously the absolute maximum, well then this is now both an absolute maximum and a local maximum. The next one says, if there is an open endpoint at what would normally be an absolute extrema, then there is no absolute extrema of that type, max or min, whichever is applicable. So to kind of explain this one, I need to give our graph some y values. But let's just say that this highest y value is actually an open dot instead of a closed one. So I put a scale on here just so that we could start to look at some stuff, and then we can actually start to assess, just because we have a y-axis now, we can start to assess some extrema. So for instance, there's a local maximum at what looks to be like 6.5, so I would just say 6.5. There's 2 local minimums, right? One of them is at what looks to be -4, and then the other one is -5.5, which is, by the way, also our absolute minimum, right? We already talked about how that's in this situation. It's doubling as both absolute and local. But then when you start to consider what is this point, it looks like it's 9, but it's an open dot at 9. So then it's not 9. So what should we say that it is, right? We can't say 8, for example, right? 8 would be right here, but there's definitely stuff higher than 8 inside of there. So typically the argument goes like this. Well, if it's not 9, it's got to be 8.9, right? That's the highest point. To which I would say, well, but 8.99 is bigger than 8.9, so it can't be 8.9, it's got to be 8.99. But then you could say, well, isn't 8.999 bigger than 8.99? And I would say, oh my gosh, you're right. So it can't be 8.99, it's got to be 8.999. And then I would say, well, wait, isn't 8.9999 bigger than 8.99? And you can kind of see where this is going. As it turns out, we can't write or say what the closest number to 9 is. So we're just going to say there is no absolute maximum. And then the last one I put on here is that arrows at the ends that point up or down imply that there's no absolute max or min, respectively. So if I do this, notice this did not change. There's still no absolute maximum in this case because it's unbounded, right? It goes to infinity. And infinity, you could always say a bigger number to someone giving an explanation for what the highest point could be. So it's a very similar argument, actually, for why we would say there's no absolute maximum. So that's it. That's the definition of all of them. Those are the special notes. Let's look at some examples. All right, example number 1. Find the absolute and local extrema of this, what looks to be a truncated parabola. Okay, let's just go in order here. Local maximum, I'm looking for hills. I don't see any hills. I'm going to say there's no local maximum. Local minimum, I'm looking for valleys. I do see that. Right, it looks like it's at -3, and in fact, -3 also looks like it's the lowest y value overall, so we're going to say that's also an absolute minimum. The absolute maximum would be 3 if it weren't an open dot here, but because it is an open dot, we don't know how to say what the closest number to 3 is without being 3, so again, we would say there's no absolute maximum, because the endpoint that would be the absolute max is an open dot. And also, just to point out, if this one was an open dot, it actually wouldn't change anything because that endpoint is neither a hill nor a valley, nor the highest point, nor the lowest point. So being closed or open doesn't actually affect anything for this graph. All right, example number 2, again, find absolute and local extrema. We'll go in order. I do see a hill here. So I would say there's a local maximum at the height of that hill, which looks to be 5, and there's a local minimum at this valley. I said negative 2.4, but if you had put negative 2.5 or something like that, then that's totally within reason. Absolute maximum, there is a highest y value here. It's 11, but then there's an arrow pointing down on the left-hand side, so we'd say no absolute minimum. All right, that's a quick one. Example number 3. All right, for this one, I'm going to give you a second. What I'd like you to do is pause the video and see if you can figure this one out. All right, let's go through this one. I'm going to start with local maximum, looking for hills, and I see 2 of them. 4 and 8.5 are the 2 that I put. Right here and right here. Local minimum, looking for valleys. I see, again, 2 of them. I went with 0 and negative 0.8. But if you went like negative 0.9, negative 0.7, like those are all within reason. And then I also noticed that this particular minimum, which is negative 0.8, is also the lowest y value. So I also recorded it for being an absolute minimum. Absolute max, I said none, right? Because the highest point is an open dot. Now I think, and I wanted to do this example for a specific reason, it's not this. I think a lot of students will see, oh, it's not this open dot, so it's the next highest point, right? And then they go to the next whatever maximum that exists was. But it's not this one because there are definitely y values bigger than 8.5, like 10 is bigger than 8.5. So just by having your highest point be an open dot, you've already fallen into the, well, how do we say what the closest number but below that is? And we don't know how to say it, so we'd say no absolute max. Okay, so that's actually it. This is one of those cases where it's very complex to describe everything mathematically, but in practice, it's fairly straightforward to do. And I think that you're going to find the same is true for end behavior when we get there as well. So hope you guys learned something. If you guys have any questions, just leave a comment below or shoot me an email. Thanks a ton for watching, and I'll see you in the next one.